Welcome, everybody. It's my pleasure to introduce Nicolò Zava. The title of his talk is Stable Invariants of Finite Metric Spaces Create False Positives.
Thank you very much for the introduction. Hi, everybody. And thanks, of course, to the organizer for the opportunity of presenting my work here in this session, in this seminar. So first, a rough sketch of what I'm going to talk about. So I will focus for half of the talk on providing definitions and motivation for the result. This part will culminate in the formal statement of the result I proved, and the final part of the presentation will discuss techniques that have been applied. All the details can be found on a preprint that I've recently uploaded on Archive. So let's recall some basic definitions. So if we have two subsets of a metric space, here we have the circle in blue and a sampling of the circle, some red dots, some finite number of red dots. Pardon. So the circle in Y and the red dots in Z, and we say that the Hausdorff distance between these two subsets is at most epsilon if growing balls of radius epsilon around Y, we contain the entire Z. And symmetrically, if we grow balls around the red dots, we contain the entire circle, the entire subset Y. The Hausdorff distance will be the infimum of all those. But what if we have arbitrary metric spaces? So let's start with two arbitrary metric spaces, let's say compact, for reasons that I'll explain later. So we have X and Y, and the Gromov-Hausdorff distance between them is defined as follows. So take X and Y, find another metric space Z in which you can embed both of them isometrically, and over there compute the Hausdorff distance. The best possible value that you can achieve by this process is going to be the Gromov-Hausdorff distance between X and Y. So this metric space, it's kind of a mysterious, this metric space Z is kind of a mysterious object. But there are nice constructions, so at least its support is not that weird. Anyways, this distance is actually a metric if we restrict ourselves to consider compact spaces. So it is known that if X and Z are compact, then the Gromov-Hausdorff distance between them is 0 if and only if X and Y are isometric. And therefore, the space of isometric classes of compact metric spaces endowed with a Gromov-Hausdorff distance, it is actually a metric space. And it's sometimes called the Gromov-Hausdorff space. So the initial interest in this metric was due to comparing metric structures from the topological point of view, especially Riemannian metric structure on a manifold. However, and that's the reason why it was introduced by Edwards and rediscovered by Gromov. But recently, its role in computational topology was emphasized, in particular in shape matching and shape recognition. However, there is a major issue with using Gromov-Hausdorff distance for computing these resemblances. And it's the known fact that computing the Gromov-Hausdorff distance, even between finite metric spaces, is a NPR problem. A possible way to overcome this problem and to approximate this Gromov-Hausdorff distance is using invariants. So instead of considering the Gromov-Hausdorff space, we send this Gromov-Hausdorff space into some nicer metric space in which either we can perform some analysis or these invariants are easily computed. But this map, this psi here, this invariant, is not an arbitrary function. We don't want just a function. We usually ask it to be stable. And here I'm borrowing the definition from memory. And this invariant is stable if the distance between the invariants is bounded by some function of the distance, of the original distance between the two associated metric spaces. In a sense, so this function rho plus can be whatever, but to give you examples, it can be a linear function. And so in that case, this invariant is a Lipschitz map, but can be also different. In a sense, we want that if the Gromov-Hausdorff distance between two metric spaces is small, then also the distance between the invariants is small. We don't want, so this invariant should detect whether two spaces are close to each other, are actually similar. This is somewhat correct, not entirely correct, because this small here is not precise. This function rho, as I said before, can be really whatever. We can have a function that goes to 100,000 immediately after 0. And so it doesn't really bound much the distance between the invariants. More precisely, we may say that stability ensures that the larger this distance is, the larger the distance between the invariants is, then the larger the distance between the original spaces. So we want stability in order to avoid these false negatives. So we want to avoid the situations in which the distance between the invariants is extremely large, but the distance between the original spaces is actually small. So we want to avoid this kind of situations. However, false positives may be acceptable. And by false positives, I mean situations in which it fails, this invariant fails to distinguish, to determine that two spaces are extremely different. So situations in which the Gromov-Hausdorff distance between x and y is large, but the distance between the invariants is small. So let me go to let me go to some examples. Let's start with some easy examples and consider the diameter. The diameter is a stable invariant. So the diameter associates to every metric space, to every isometric class of metric space, their diameter. It is stable. And actually the function here is Lipschitz, is a Lipschitz function. So the coefficient is just 2. But of course, this function actually loses a lot of information and it creates lots of false positives. Here I have an example. You have the diameter of x is equal to the diameter of y, but if we let a, the parameter a, increase, then the Gromov-Hausdorff distance between these two spaces actually tends to infinity. So we have situations in which these spaces are as far apart as you want, but the diameter is going to be the same. So now you may argue, well, the diameter, we didn't have high hopes about the diameter, but can we maybe refine our investigations. And what if we consider the entire distance set? So instead of taking the maximum distance within the subset, within the metric space, let's take all of them. Well, this is again a stable invariant. Again, we have a function, a very particular function as a bound, like the multiplication by 2. So it is stable. However, again, we have false positives. We have Bloom constructed 2 finite metric spaces, actually 6-point metric spaces, that have the same distance set, but they are not isometric. And therefore, they have positive distance, and we can rescale these examples as big as we want to obtain something paradoxical, as in, not paradoxical, pardon, like something unwanted. So we can obtain spaces whose Gromov-Hausdorff distance is as high as we want, but they have the same distance set. And the same happens with persistent diagrams induced by, for example, the Vittori strips filtration. This is a stable invariant in the sense that the bottleneck distance between the persistent diagrams induced is bounded by twice the Gromov-Hausdorff distance. But again, it's quite easy to produce false positives, spaces in which the pair of spaces whose Gromov-Hausdorff distance is as high as we want, but they have the same persistent diagrams. So the question is now, is it always the case? Is it always the case that if we require stability, then there are false positives? Or is it just that we haven't found yet the right invariant? So this is the question I wanted to address. So can we find stable invariants that avoids false positives? So this is a vague question because I haven't given you the precise definition for me of avoiding false positives. So taking inspiration from the stability that avoids false negatives in that weak sense that I described you at the beginning, we can say that an invariant avoids false positives if the distance between the invariants is bounded from below by some function of the distance between the Gromov-Hausdorff distance between the metric spaces. There is a technical requirement here asking that rho minus has to tend to infinity, but without this, otherwise everything, I mean, every invariant satisfies this inequality. You could just take rho minus to be the constant 0, and so no information actually is provided. So again, in a sense, the inspiration comes from the fact that this inequality implies that if the distance between the invariants is small, then small must be also the distance between the Gromov-Hausdorff distance between the metric spaces. Again, this is not so true. I mean, it has to be taken with a grain of salt because the function rho minus can stay 0 for quite some time before starting increasing very weakly. So it's a weak formalization of the notion of avoiding false positives. Again, more precisely, we say that this lower bound actually tells us that the larger the Gromov-Hausdorff distance is, the larger the distance between the associating invariants. Okay, so now we have our formal question. Do there exist a metric space X an invariant from the Gromov-Hausdorff space, and two functions, rho minus and rho plus, called control functions because they control the distance between the invariants, such that actually this inequality holds for every compact metric spaces, or every pair of compact metric spaces. So again, we have a bound from below and a bound from above, depending on the Gromov-Hausdorff distance. And the answer is, even though actually rho minus and rho plus they do not have to be Lipschitz functions. They do not have to be constant functions. They can be whatever. So it's quite weak as a requirement. The answer is going to be still no. If we want X to be, if we want to be the target space, a Hilbert space. So it's not a matter of we haven't found the right invariant yet, that this right invariant cannot exist. How can we prove such a thing? We need to use tools from coarse geometry. Coarse geometry is a branch of metric geometry that studies actually the large-scale properties of spaces, ignoring like small local perturbations, small variation of the spaces. So I've recalled the Gromov-Hausdorff distance. For this theory, if two spaces have finite Gromov-Hausdorff distance, then they are essentially the same object, because they are modifications. I mean, with local changes, you can get from one space to the other. So for this point of view, they're kind of the same object. And therefore, for example, in this theory, all finite metric spaces are the same object. So it kind of collapses a lot, but not everything, because there are spaces that are, for example, the plane is different from the real line. But I don't want to go into details about coarse geometry. It's not the aim of the talk. I just wanted to give you like the idea of what's the philosophy of this branch. Anyways, there are also spaces that are coarsely equivalent, that are the same for this theory, but whose distance is infinite, whose Gromov-Hausdorff distance is infinite. What's interesting for us are the morphisms in coarse geometry. So the morphisms in this theory are sometimes called Bernoulli maps or coarsely uniform maps. These are maps between metric spaces for which the distance between the target space, between images, it is bounded from above by some function of the distance between the original space, the original points. And actually, this basically is stability. The stability I recalled at the beginning. So these are the morphisms, and the embeddings in this theory are called coarse embeddings. And these are precisely what we've seen before. So these are maps for which there are two control functions that bound both from above and from below the distance between images of points. So actually, the notions that I've previously defined are the same as these notions known in coarse geometry. But what are the techniques that we may use? So a bit of history. So one of the fundamental applications of coarse geometry in the realm of index theory is this result to Yu, who proved that the metric spacing admitting a coarse embedding into a Hilbert space satisfied the Novikov and the Coarse-Baum-Kohn conjectures. So the natural question is, are there metric spaces that do not admit a coarse embedding into a Hilbert space, or it's just it is just a like a fake hypothesis? I mean, like every metric space satisfies this. Well, the answer is no. Not every metric space admits such a coarse embedding. And the first example is due to Anishnikov, Gom, Laforgue, and Yu. And so using this example or other that came later, we have a tool to prove that a certain metric space Y cannot be coarsely embedded into any Hilbert space. Why? Because how can we do that? If we find a coarse embedding from X from one of those pathological examples, like for example the one from Danishnikov, Gon, Laforgue, U, that cannot be coarsely embedded into any Hilbert space, but it can be coarsely embedded into Y, then Y cannot be coarsely embedded into any Hilbert space, because otherwise we could just compose the two coarse embeddings and obtain a coarse embedding from X to a Hilbert space, which is a contradiction.
Nicolò,
This technique, pardon? Yeah,
can I have a question?
yeah, sure.
Yeah. So what is Novikov and the Quartz-Baum conjecture? Is that something we need to know, or too complicated? No?
These are very, very technical conjecture. It has to do with the injectivity of the coarse assembly map in between higher. So it's very complicated. It's something that I should know, and at some point I will learn.
Okay.
But it's very, very, very deep theory behind.
Okay, not for now. Okay.
Not for now. No, definitely not for now.
Okay. Okay.
Thanks for the question.
Mhm.
So this technique that I've just described actually has been applied before to prove, for example, that the space of persistent diagrams endowed with various metrics cannot be coarsely embedded into any Hilbert space. This was proved, I mean, changing the matrix by Carrère and Bauer, by Atish and Giga, and by Wagner. It was also proved with Thomas and Takamitsu. We also proved that the space of finite subsets of, let's say R, in reality any geodesic unbounded metric space, but for the sake of simplicity, you can consider R. So you add R, and you have the family of finite subsets with the Hausdorff metric, not the Gromov-Hausdorff, but just the Hausdorff metric. This cannot be coarsely embedded into any Hilbert space. Using kind of the idea we developed in that project, I'm working with Alexei and Giga to improving that the space of periodic point sets that actually represent crystals, they are the generalization of lattices with the Euclidean bottleneck distance, again, cannot be coarsely embedded into any Hilbert space. So now let's
Nicolò?
go. Yes.
I see there's a question in the chat. Can you see the chat, or would you like me to read the question?
If the space is gonna. What function space can you embed your space into? So you say something like a Kuratowski-like embedding. I'm not sure I 100% understand the question. What I can say, so let me first read out loud the question. So the question is if the space is not coarsely embedded into in a Hilbert space, then what function space can you embed your space into? So there is a problem with the distortion. So of course you can always embed your space like how can I say that? Saying like that every point is going to be like the characteristic function of that point of the singleton, but still there is a problem with the metric, because it's going to be probably too big as a space to be metrizable, or it's not going to be Hilbert. I mean, it's quite restrictive, to be honest, to say that the target space is a Hilbert space. I mean, it is justified because we may want to perform some analysis. Vectorization of spaces is really an important thing for machine learning algorithms and for other things, but it's still quite restrictive to only consider Hilbert space and not, for example, Banach spaces, because then with the space of functions, you can put this in the space of function, for example, the supremum metric, but the supremum metric may not be a Hilbert distance. And so these are the problems with this kind of canonical embedding into function spaces. I'm not sure I completely understood the question, or I addressed it. If not,
can I add a few more sentences?
Yeah, sure.
On the same topic. So, in general, any metric space can be embedded in L. Let's say X is a metric space that can be embedded in L infinite of X, which is by Kratovsky embedding, and which is a function space using supremum norm. Moreover, L infinity space is actually an example of so-called injective metric space, or equivalent to hyperconvex space. It is a space having some very nice properties. It has some similarity with negatively curved spaces, and moreover, X can be embedded in not only L infinity of X. X can be embedded in smallest possible injective spaces, that is so-called injective hull, injective envelope, or tie span, and that is another function space we can embed X into. But of course, that is using L infinity norm, so it's not a Hilbert space.
Mm-hmm.
Yeah, but it's very general. Yeah.
Yeah. Thank you very much for the point you made. Yeah. Okay, so now going back to our main goal, so the Gromov-Hausdorff space, but still we have the problem that the Gromov-Hausdorff distance is hard to compute. Also, for example, so constructing this coarse embedding from one of those examples to the Gromov-Hausdorff space is not going to be easy. So what if we consider some modification of the Gromov-Hausdorff distance? So what if our metric spaces are not arbitrary metric spaces, but they are actually subspaces of some R to the n? Then, instead of considering any embeddings into any metric space, let's just consider embedding into R to the n. So as in this picture, we have X and Y that are subsets, are subspaces of R2, and we just look for embeddings, isometric embeddings into R2. This is and then take the Hausdorff distance there and minimize along for all possible embeddings. It's somewhat called the Euclidean Hausdorff distance, or it is the Hausdorff distance under, so Hausdorff under isometry distance. So it's a bit easier because we know a bit more about R to the n. We don't have to look for weird metric spaces. So we have a bit more hope of constructing the coarse embedding we want. Let me give you also another characterization of this distance. So the distance between x and y is actually going to be the infimum of over all isometries of r to the n between the Hausdorff distance between f of x and y. So as in these pictures, we can somehow translate and rotate the plane in order to achieve a nice matching between the two pictures. And that's the same, they give the same value. So we have the space EH, like in the flavor of the Gromov-Hausdorff space. We can consider the space of isometry classes, of compact subsets, of some r to the n, with the Euclidean Hausdorff distance. And of course, there is a canonical inclusion, because every isometry class of compact subsets of r to the n is a metric space, is an isometry class of metric spaces themselves. So it is natural to ask, what are the properties of these inclusions? Is this inclusion maybe a coarse embedding? And so can we use this, can we study EH, the space EH, to obtain information about the Gromov-Hausdorff space? Well, what is always true is this upper bound. The Gromov-Hausdorff space, the Gromov-Hausdorff distance is always bounded from above by the Euclidean Hausdorff distance. Why? Because the Euclidean Hausdorff distance is kind of lazy. It searches for embeddings only into some fixed metric space, whereas the Gromov-Hausdorff distance can achieve better results by sending the metric spaces into other mysterious metric spaces. So the real question is whether there exists a lower bound to the Gromov-Hausdorff distance, a uniform lower bound to the Gromov-Hausdorff distance. And in general, the answer is no. I'm taking this example from a paper of memory. So if we consider regular simplices with edge length 2, and so this is going to be our first space, and the second space is going to be just a singleton. In the Euclidean space, in R to the n, the best you can achieve is putting your singleton in the center of the simplex. Therefore, the Euclidean Hausdorff distance, however, the Euclidean Hausdorff distance is gonna increase with the increasing of the dimension of the simplex in such a way that the Euclidean Hausdorff distance will tend to infinity with growing the dimension of the simplex. However, the Gromov-Hausdorff distance is going to be constant. So it does not depend on the number of vertices of your simplex, on the dimension of your simplex. Why? Because you can send, let's just consider, for example, a triangle. You can send this triangle here isometrically into a tree with the path length. And the distance, so this is an isometric embedding, and the distance that can be achieved is actually 1. You can increase the number of branches to accommodate every dimensional simplex, an n-dimensional simplex, obtaining the same Hausdorff distance, Gromov-Hausdorff distance. Therefore, this map is not a coarse embedding. So, okay, our first shot missed. That's fine. But we see in this example that we need to increase the dimension of R to the n of the Euclidean space to contain simplices of higher and higher dimension. So the second question would be, what if we restrict to consider compact subsets of R to the n for some fixed n? Well, the results we have, the lower bounds we have, prove my memory again. So we have some lower bounds depending on the Hausdorff distance. The problem is that this constant m, which is going to be the maximum of the diameter between the two metric spaces. Therefore, this lower bound function, this control function that serves as a lower bound, is not independent of x and y, so cannot be totally uniform. This is not a coarse embedding. It's not enough to say that this is a coarse embedding. So again, our second shot missed, but what if instead of r to the n, we just consider r, subset of the real line? So is the restriction to this very small space a coarse embedding, at least? And the answer is finally yes. Magic, Victor, and Bank provided actually a linear lower bound to the Gromov-Hausdorff distance, depending on the Euclidean Hausdorff distance. And in their paper also, they proved that this lower bound is tight, so it cannot be achieve any better result. So we have, in this case, we have that this map here is not just a coarse embedding, but it's extremely nice, and it's a bi-Lipschitz embedding, a particular case of coarse embeddings. So now I can state the major result, the major technical results, saying that the space consisting of isometry classes of finite subsets of the real line with the Euclidean Hausdorff distance cannot be coarsely embedded into any Hilbert space. And from this result, the result for the Gromov-Hausdorff space, or even for isometry classes of finite metric spaces with the Gromov-Hausdorff distance, actually follows, and immediately follows, because suppose that, for example, the Gromov-Hausdorff distance can be embedded into a Hilbert space, but we show that, I mean, using this result, this embedding here is a coarse embedding. Of course, this is just an inclusion. This is just an embedding, an isometric embedding. So this thing here is going to be a coarse embedding. If we compose it again with a coarse embedding, we would obtain a coarse embedding from this space to a Hilbert space, which is actually a contradiction. And so we obtain the corollary, and we can rethink the corollary in the terminology we used at the beginning, and say that every, as the title says, every stable invariant with values, taking values in a Hilbert space, returns false positives. So it's not a matter of finding a nice invariant. You cannot avoid false positives if you want a Hilbert space as a target space. To be more precise, we can say something a bit more stronger, and we can say actually that this space cannot be coarsely embedded into any uniformly convex Banach space. So it's a I don't want to give the definition. I mean, it's just a somewhat a generalization of a Hilbert space. So this is the result, and I think I have a few minutes to describe the main construction, if I can. Okay, good. So the idea, the fundamental lemma would be take any family of finite metric spaces. It's like our pathological example that we want to embed in this space here. Consists of a family of finite metric spaces that are coarsely embedded that are in our case will be by Lipschitz embedding into this big metric space in such a way that the distance between the pairwise distance between these spaces, these finite spaces, these finite pieces, will tend to infinity. So they are scattered around my space. So I will not describe the entire situation, the entire construction. Let me just show you how to embed a singular piece. It's like a finite metric space in our metric space, in our subset, as subsets of the real line. So take your favorite metric space. Using the Kuratowski embedding again, we can basically isometrically embed it into a cube, a finite cube with, I mean, not a finite cube, but a finite dimensional cube. So we can restrict ourselves to consider just these guys. So cubes like an interval to the power with a supreme metric. So something quite tangible, something that you can actually work with. And so now we can take x1, xn, a point in the cube, and we produce a subset of the real line the following way. So we take a sufficiently long interval, and we take a distance. A1 is going to be 0, but I mean a distance x1 going to be take a red dot, some blank space, some sufficiently large blank space, and then a distance x2, another red dot, other blank space, and so on and so forth up to xn. After that, you leave again some blank space, some quite big blank space, and put another dot, another red dot here. So basically, we took our cube and we laid down all the dimensions to obtain a finite subset. I don't want to. So let me point out a couple of things. First is that this upper bound is quite easy to see. Why? Because suppose you have x1, xn, and y1, yn. So two elements of the cube. Then already the Hausdorff distance between the red dots and the blue squares is going to be the original distance. Why? Because these blank spaces are big enough. So the distance, actually, the best possible matching will be achieved between either x1, x1, y1. So x1 will be paired with y1, x2 with y2, and so on and so forth. And the distance will be actually the maximum. The Hausdorff distance is going to be the maximum between these pairwise distances. The second thing I would like to point out is that this construction up to this point actually is borrowed by the project I conducted with Thomas and Takamitsu. The real difference is this final point. The role of this finite point is to disincentivize the role of isometries, because we are not working anymore with the Hausdorff distance. We work with the Euclidean Hausdorff distance. And so we make, I don't know, like shift our red dots to achieve a better matching. But the existence of this final dot common to both of them actually creates misalignments as soon as we translate the subset. So this just to give you an overview of the construction. Future directions. Here in the construction, I've said that I need sufficiently large intervals. So what if we consider, instead of metric spaces of arbitrary diameter. We put a uniform bound on a uniform upper bound on the diameter of the metric spaces. Well, that's very interesting. That's a valid question. Coarse geometry is of no use. Why? Because if both x and y have diameter bounded from above by r, then also their Gromov-Hausdorff distance is going to be bounded by r divided by 2. Which means that the entire space is going to be bounded. And from what I said at the beginning, like when I introduced coarse geometry, for coarse geometry, bound is trivial. It's just a point. So coarse geometry cannot say anything. However, we can use other techniques. We can use, and that's actually our goal for the project, for the future development of the project. We can use other techniques to maybe find problems for by Lipschitz embedding, for example, and those kind of things. The second question, and the second direction we are pursuing is, what if we do not consider arbitrary metric spaces or arbitrary subsets of the real line, finite subsets, but we put a bound on the cardinality. So we say like spaces, metric spaces of at most n points. Can we say something? That's going to be the next the two next directions that we want to investigate. And with it, that's it. Thanks for the attention.
All right, I suggest that we all unmute ourselves and give a round of applause. I see that there's a question in the chat, and David, also feel free to unmute yourself and ask your question if you'd like, but
from the previous theorem, I'm not sure which theorem, maybe this one.
yeah, I think it's the theorem on slide 20.
Okay. From the previous theorem, I'm thinking an answer to my question is vectorizing the target space into a metrizable space, which could be embedded into a Hilbert space. But if you I see, could that be possible? The problem I see again. So of course, thanks for the question. That's indeed interesting. The problem I immediately see is that, what do you mean by vectorizing? And what are the properties, the metric properties you want to retain by vectorizing? Because if your vectorization is going to be a coarse embedding, that you are not improving the situation. I mean, you're not escaping from the loophole we are in, because if you embed into some vector space and then with some metric, and then you put a metric in it, and you embed it again into a Hilbert space, and then again, what are the constraints on these embeddings? If you want it to be a coarse embedding, that again, by composing everything, you will have a coarse embedding from the original space into a Hilbert space, and therefore this is not possible. What it means is that you will need to lose information somewhere, or lose some information. I mean, it's not gonna be a disaster. Persistent homology is extremely useful, even though it creates false positives. So again, it's a trade-off between precision and computability. Or you may want to not use Hilbert spaces, but Banach spaces. And so you, for example, recall with the Kuratowski embedding or the tight span. So there are ways to overcome this problem, I'm not saying that you cannot do anything with the Gromov-Hausdorff space. It's just that you cannot do these kind of things, like these nice, even though it's a bit lax as constraints, but you cannot perform these embeddings into Hilbert spaces. So you can either lose information throughout the project, throughout the process, or choosing other target spaces. Not sure I completely answer the question, but thanks again.
Okay, so thanks for answering the question. But my question, I'm actually enthused by the inclusion map there. If you look at the theorem, you have two inclusion maps. That's from the embedding. You have one to the Gromov-Hausdorff space, and another inclusion map that is embedding the Gromov-Hausdorff space to another Gromov-Hausdorff space before actually embedding to the Hilbert space. So what are the functions of the inclusion maps there?
The inclusion map here is just, here we just consider finite metric spaces, which is included in compact metric spaces. They are just a subset of compact metric spaces, of the space of compact metric spaces. So that's the inclusion, like real subspace of the Gromov-Hausdorff space.
Oh, okay. So the two inclusion maps, do they have different properties?
Yes, this is a by Lipschitz map for this result here. Says that this inclusion is not really an inclusion in the topological sense, but we can see like a subset of the real line is just an example of a finite metric space, but we change the metric. But this is a by Lipschitz embedding. This is an isometric embedding. So all of them are example of coarse embeddings. Even the composition of them is going to be a coarse embedding. And therefore, if we could, this is just a representation of the deduction from this theorem of this corollary. If we had a coarse embedding from the Gromov-Hausdorff space into a Hilbert space, then by composition, we would have a coarse embedding from this space into a Hilbert space, and therefore a contradiction. So this is just a representation in order to justify the corollary and to see how easily it can be derived.
Okay, thank you.
Thanks to you.
I think we have time for maybe one more question, on the recording at least. Are there more questions for our speaker?
I was hoping to ask a quick one, or I really like this framing of false positive, false negative. Of course, I'm familiar with the underlying stuff, but I never heard this framing. I like it very much. But I did have a question. How did you decide which was false negative and which was false positive? And I'll give you my reasoning. Okay. In data science, we often want to ask the question, for example, you want to do t-test. Are two populations different? In that case, positive is the populations are different, negative is they are the same. In that case, this is the wrong way around for your analysis, right? So I just wondered what the thought process was, how false positive, false negative came to be.
Okay. So again, we want to, where is it? Oh, first, let's stay here. So the question here would be, are these two spaces, X and Y, similar? So the positive would be yes, and the negative would be no. A false negative, you have a false negative if two spaces are actually similar, but your invariant fails to detect it. The associated invariant are very different. You have a false positive if two metric spaces are actually very different, but your invariant will tell you, no, they are kind of the same object.
Okay,
So
that makes sense.
that's the question. So
Yeah.
are they similar?
I think you may find some statisticians are very will push back on that point, but it's fine to me. I understand.
I see. Oh, thanks. I would frame it the question very clearly then. Thanks.
All right, well, thanks everyone. I'll go ahead and stop the recording here.